We want to find the sum of a geometric sequence, or in other words, find a geometric series. To do that, let's look at the properties of what this geometric series is going to look like. So here I have a geometric sequence, 16, 24, 36, 54. We're multiplying by 1.5. So let's just make sure that's clear. R is equal to times by 1.5. And when I add up this sequence, in other words, get a series, so 16 is the first term, so S1 is same as T1, S2 will be the sum of the first two terms, S3 is the sum of the first three terms, etc. And when I graph this, I end up with a curve that kind of looks like this. And this progression, if we take a look at this curve is curving up, and in fact is an exponential curve. So the geometric sequence is an exponential sequence, but the sum of the geometric sequence, or the geometric series, is also exponential. Well, how do we get this exponential expression? So this is the formula for the sum. So as long as r is not equal to 1, so as long as our multiplier is not 1, we can use this formula to generate the sum, or the addition of all the geometric sequence terms. In other words, a geometric series. So how do we come up with this formula? And recognize that the formula, this part here, makes this an exponential function. Okay, our input is n, output is Sn. So let's take a look at this. So if I take a geometric sequence, the geometric sequence in term by term looks like this. So first term plus second term plus third term, all the way to the last term, which we show by ARn minus 1. And what we've done in the second line is we've multiplied the first line by r. So what that will do is it will just shift every term. So a becomes AR becomes AR squared, and the last term, AR n minus 1 times by r equals ARn. And so if we take a look, there are some matching terms here. And if there's matching terms, and in fact all the terms inside match, if we subtract these expressions, so I take the bottom line and I subtract the top line, everything cancels out except for these two terms. So that's what we've done here. We take the r times Sn, that's the second line here, and maybe I'll just show that. So we take that line, and what's going to be left over, what doesn't cancel out, will be just that one term, and we're going to subtract this line here. And everything that doesn't cancel is going to be that a, which ends up as minus a. And if we simplify this expression, we're just going to factor out the Sn from this expression, so we end up with r minus 1, and we factor the a out of this expression. And really I'm trying to solve for Sn, which is the sum of all the terms. If I divide both sides by r minus 1, I end up with the formula for my geometric series. And there it is. There's the formula for my geometric series. And this formula is an exponential function. So when I actually graph the series, I get an exponential curve. And this is actually quite unique. And the geometric series is the only type of progression where the changes, so the changes will be reflected by Tn. So this is plus Tn, where the changes of this progression, the changes actually mimic the actual function. So this is an exponential function. The changes are also exponential. This did not happen with the arithmetic series, because when we looked at the arithmetic series, the series was quadratic, but the changes, how the Tn chain is added on, the changes were linear. And that's something that we were alluding to in some other units.